Dear sir, madam, and everyone, I am Ngọc Nguyễn from Vietnam. Today, I'm very honored and happy to present my research conditional mixture model for modeling attributed dyadic data. Abstract dyadic data contains co-occurrence of objects with the often model by finite mixture model, which in turn is run by expectation maximization EM algorithm. Objects in traditional dyadic data are identified by names, causing the drawback that it is impossible to extract implicit variable knowledge under object. In this research, I report the so-called attributed dyadic data, in which each object has an informative attribute and its co-occurrence of the object is associated with a value as is flexible and cover most of structure form of dyadic data. Conditional mixture model CMM is which is a variant of finite mixture model which apply into learning. Moreover, a significant feature of CMM is that any co-occurrence of the object is based on some conditional variable. As a result, CMM can predict or estimate co-occurrence values based on regression model, which extend application of ADD and CMM. Table content 1. Introduction to dyadic data and mixture model. 2. Learning attributed dyadic data S by conditional mixture model CMM. Conclusion. 3. Conclusion. 1. Introduction to dyadic data and mixture model. Simple data has two parts, such a hidden part S and observed part Y, and we only know Y. A relationship between random variable S and random variable Y is specified by the John probability density function BDF denoted by f of sy given theta, where theta is parameter, given sample y1, y2, yn, whose on yi are neutral, independent, and identical distributed IID. This is required to estimate theta based on such sample where is SE unknown. Expectation maximization EM algorithm is applied to solve this problem when only yi are observed. EM has many iterations, and each iteration has two steps, such as expectation step, and maximization step, M step. As some t iteration given current parameter theta t, the two steps are described as follows. Next slide. Each step, the expectation Q is determined based on the current parameter theta t according to equation 111. As step, the next parameter theta t plus 1 is a maximize of Q, which subject to theta. Not that theta t plus 1 will become current parameter at the next iteration. EM algorithm will converge after some iteration. At that time, we have the estimate theta t equal theta t plus 1 equal theta star. Not that the estimate theta star is the result of EM. Given two finite set S and Y with not dash Si and Yj represent S of Z and Y of Z respectively. Exactly, they are names of objects. An observational pair Si Yj is called the co-occurrence of Si and Yj. Dyadic data or co-occurrence data S contains the co-occurrence with not that a co-occurrence Si Yj can exist more than one time. So its co-occurrence is indexed by an index R. As a result, its co-occurrence is denoted by the triple SIYJR, and we have the equation 112. Object. Its object. Of course, the sign of S is the cardinality of S. As a convention, SIR and YJR indicate that S of Z and Y of Z are the co-occurrences are SI and YJ respectively. Thus, the triplet SI YJR can be denoted as SIR YJR. Simple its co-occurrence belong to the latent variable C, and C has the K value CK. These values CK are called last or aspect, and thus mixture model for dyadic data is also called aspect model or latent last model, which aim to discover the latent variable C without loss of generality. Let CK equal K. The random variable C has a discrete distribution such that every value has an associated probability alpha K. Of course, there are the K probability alpha K. There are three kinds of dyadic mixture model for dyadic data such as symmetric mixture model SMM, asymmetric mixture model AMM, and reduced by mixture model BMM. In this section, EM algorithm is applied to build up this mixture model. SMM, AMM, and BMM are mentioned in the next slide. Symmetric mixture model SMM is defined by equation 1.3 by applying EM given dyadic sample S at some t iteration given current parameter theta t. The next parameter theta t plus 1 of SMM is calculated at f step according to equation 1.4, 1.5, and 1.6, where n SI denote the number of co-occurrence of SI YZ. The conditional probability P of K is calculated at each step according to base rule as seen in equation 1.7. A symmetric mixture model AMM implies that alpha K are only independent from SI or from YZ, which is defined by equation 1.8 by applying EM given the sample S at some t iteration given current parameter theta t. The next parameter theta t plus 1 of AMM is calculated at m step as equation 1.9, 1.10, and 1.11. The conditional probability of AMM is calculated at each step by equation 1.12. Produced by mixture model BMM is derived from SMM with a minor change that the aspect 1 2K is the Cartesian product of a space set and Y space set. In other words, the space space is still symmetric but it's adjusted according to two directions X and Y according to equation 1.13. For every K belong to 1 2K, the only exist a quadratic pair Kx and Ky. However, for each Kx or each Ky, there are many quadratic K as equation 1.14. The sign title denote the corresponding BMM is defined by equation 1.14. By applying EM given dyadic sample S at some t iteration given current parameter theta t, the next parameter theta t plus 1 of BMM is calculated at m step mentioned in the next slide with equation 1.16, 1.17, and 1.18. The equation 1.16, 1.17, and 1.18 determine the next parameter theta t plus 1 of BMM which is calculated at m step. SMM, AMM, and BMM are defined in terms of traditional dyadic data. The next section is the main subject of this research, where the so-called attributed dyadic data S is modeled by conditional mixture model (CMM). In dyadic data S, if it co-occurrence of Si and Yz is associated with a value Z, the triple SI-YZR become the quadruplet SI-YZ-ZR, which is called the value co-occurrence of SI and YZ. The value Z is called associative value of co-occurrence value. See equation 211. If Z is value of a variable Z, then Z is called the associative variable. As a result, the symbol S is called value dyadic data. Not Z can be univariate or multivariate vector. As the convention ZR indicate that the associative value at R co-occurrence is Z. Thus, the quadruplet SIYZ ZR can denote as SIR YZR ZR. An extension of value dyadic data is called attributed data. In every X has an attribute SI and every YZ has an attribute YZ, which concern that on SI are IID and on YZ are IID. Of course, the attributes are considered as a random variable. Let S and Y be random variable representing every SI and every YZ respectively. Not S and Y can be univariate or multivariate, which are called attribute variable. As a result, the symbol S is called attributed data S. Attributed dyadic data S. The convention SR and YR indicate that S of Z attribute and Y of Z attribute at the are co-occurrence respectively, where ZR indicate associative variable at the are the co-occurrence. The attribute dyadic data S is represented by equation 212. Thus, its co-occurrence in attributed data attribute dyadic data is denoted by the triplet SR, YR, ZR. The S of Z and Y of Z of SR and YR are denotes SR and YR which are some SI and YJ respectively. Here is required to extend SMM, AMM, and BM to represent S. The genre probability density function BDF of S of Z attribute S and Y of Z attribute Y expect K associative variable Z given conditional variable W is thus the zone BDF of S of Z attribute Y of Z attribute A expect K and associative variable Z given conditional variable W is defined by equation 213. Of course, alpha k, beta k, gamma k, and theta k are partial parameters of fk, gk, sk, and vk respectively. The function are BDF, the whole parameter is the theta. The BDF fk if inline distribution of aspect k given conditional w, the two BDF gk and sk inline distribution of attributes with regard to s of z, y of z, and aspect k. The BDF vk is conditional BDF of just given W with regard to aspect K. Later on, we will know that it is more useful if it is considered as a regression model. According to Pascal, the conditional probability of K given S of Z attribute, Y of Z attribute, associative variable Z, and conditional variable W is defined by equation 214. Symmetric model SMM for attributed dyadic data is called symmetric attributed mutual model SAMM, which is defined based on the zone BDF F and KS bet A according to equation 215. Recall that parameter of AMM is the theta obviously SAMM is an extension of conditional mixture model CMM when FK and VK as based on the conditional W. SAMM is symmetric which is correspondent to SMM here. We focus on building up SAMM by mixture model and AM. A symmetric model and Rhodes model for S will be mentioned later. SMM represented by equation 215 will be more specific and useful if FK and GK and SK are multimodal BDF and VK is regressive BDF which represent regression model, mean and covariance of matrix of FK, GK, and SK are alpha K, beta K, and gamma K. Parameter of equation 219 are mentioned in the next line. Equation 210 specify parameter of decay mentioned in equation 219. Not A and B are dimension of Z and W mean and covariant matrix of Z given W are omega K W and sigma theta K. Equation 211 also specify the multivariate regression function with imply that by applying EM algorithm given attributed dyadic symbol as the iteration of the EM given current parameter theta t, the conditional expectation Q of SAMM specified by equation 215. Here, according to equation 214, the conditional probability B of K is calculated at each step according to equation 213. The net parameter theta plus 1 at maximize Q at f step of some iteration is solution of the equation formed by setting the fourth order partial derivative of Q with correcting theta to be 0 because FK, GK, and SK distribute normally by referring the reference phi. The next parameter alpha K plus 1, beta K plus 1, gamma K plus 1 for SMM are calculated at m step as follows according to equation 2114, 2115, 2116. Because the VK of Z is the regressive BDF known as the adaptive regression model ARM by referring the reference phi. The next parameter theta K plus 1 is calculated by equation 2117, 2118. Not A and B are dimension of Z and W. The product omega K plus 1 W is calculated by equation 2111 and equation 2.17. Equation 2.21 specify the matrix W and matrix Z. A symmetric model is not appropriate to S because the VF of aspect K, Fk become impractical if it depends on both W and S as Fk. However, the product space model BMM for S is still practical. BMM for attributed dyadic data is called product space attribution model BAMM, which is defined by equation 2.22 here. And F step of some T iteration, the next parameter for BAMM are SMA the ones for SAMM, but the next parameter for BAMM as estimated particularly by equation 2.23 and 2.24. The probability P of Ks and P of Ky are determined in the next slide. Of course, the conditional probability P of K is calculated at step according to equation 2.13 plus equation 2.20 and equation 1.21 to understand equation 2.25 and equation 2.26. CMM for S such as SAMM and BAMM can be used to estimate the unknown associative value Z given attribute variable S and Y, and conditional W. Let Z hat be estimated of Z according to equation 2.27. It's easy to calculate the conditional PDF of Z given S, Y, and W according to CMM according to equation 2.28. The estimate Z hat given S, Y, and W is calculated smoothly by equation 2.30. In general, equation 2.30 is the ultimate estimation formula of CMM for S. Conclusion: S is flexible and cover most of structure form of dyadic data. CMM for S such as SAMM and BAMM have researched to model S in flexible solid variable manner. For example, if aspects are independent from conditional variable, its PDF Fk is reduced into a discrete probability parameter. If its recipe PDF Fk is not formed in favor of regression model, it must be from a probability distribution like conditional multinormal PDF. An interesting application of SAMM is to build up a unified estimation model of content-based filtering, collaborative filtering, and context-aware filtering, in which attributes along with GK and SK are responsible for content-based filtering, while associated variables along with VK and SK are responsible for collaborative filtering and context-aware filtering. The attribute X and Y represent information about user and item in region data. We know that user and item are known as objects. The associative variable Z represent value in region data. The conditional variable W represent the context equation. 2.30 is the ultimate formula of unified estimation model. I hope that researchers will concern such robot model because it is not realized yet when I compose this paper. Thank you very much for your attention. I am very honored and happy to answer your question. There are references. The main reference is the work of Huffman, Fujita, and Jordan. Learning from dyadic data in advanced in Neural Information Processing System 11, NIPS 1998, Denver 1998. Many thanks to you again.